presentation. Okay, so I apologize, I was not there yesterday, so I don't know how many of you come from here. I'm not here. How many of you have taken QFT? QFT lectures, everyone, as a lady? Okay, and then of course the level of QFT depends on the professor, on where you learn, and books and stuff like that. Okay. So I also apologize for repeating for the 5th time what you heard about yesterday and this morning, but I'm going to try to, so it's supposed to be about PDFs. So all the school is about QCD, PDFs, and electronic correction of electronic phenomenology. So what you heard before is mainly about the observables that we have, and I'm going to try to see similar materials to go to the definition of what is a PDF and what we mean by PDF, okay? So we're going to hear again a few things that you heard before, but we're going to go a bit slower perhaps and try to get to the definition of PDF, okay? So I guess there are experimentalists, theorists, lattice practitioners, how many lattice people here? I saw you guys, yeah. Okay, experimentalists, theorists, people in all three together? Oh. Okay, yeah. Okay, so the good thing is that everything goes together. We need all three elements to try to understand what PDFs, what the proton or the pion. I will talk mainly about the proton though. Okay, so my name is Aurore Courtoy. No one can pronounce that unless you use French speaker. So Aurora, whatever you want to call me is fine. Okay, whatever you can. Sorry. Okay, so just to give you an idea of who I am, where I'm not from Mexico, but I've been in Mexico for a long time. So that's where we are. Okay, so David is there as one of my students, and Max is from there as well. So that's Mexico City, and we are somewhere here. Okay, so that's the group last month. And so I was trained in theory, like heavy theory, non-perturbative models, and then I moved to phenomenology during the first postdoc, and I never moved back. Kind of between the two, and now that's one of the pictures of the campus. It's a protected campus. It's beautiful, and that's one of the murals that we have. You know, in Mexico there are a lot of muralists, and UNAM is full of those beautiful murals. You should come one day and see them. That's the main library of the university, and as you said, and you see here, I'm building a group, and it's growing, and we're trying to do great physics. And so you can see, the reason I'm here is because of CTEQ-T and Phantomas. I will talk about Phantomas mainly tomorrow, and CTEQ-T as well, but you guys are familiar with CTEQ, I guess. Okay, so goal of the lectures, it's understand PDFs, okay? There are many things to say about PDFs, depending on who you talk about. PDFs, they will tell you one thing or another thing. Same like phenomenology. If you say that word to some people, they will tell you this is phenomenology. So perhaps I will go more into details tomorrow about what I call phenomenology. But for today, we're gonna repeat some things, okay, about PDFs from the Parton model to QCD, right? And tomorrow we're gonna talk more about inverse problems and all of the things that we can go through and all things like that. I will put some problems, homeworks in green boxes. I'm happy to discuss them today because there are things that you've seen before, or during the recitation, or whenever you like, okay? You don't have to do them, but some are really simple and some are perhaps more complex, okay? Any question? I should put my email, I forgot, okay. So non-exhaustive bibliography as well. I forgot a few things, but then, so then you will see from this literature that it comes more from non-perturbative aspects of PDFs. And there's this really nice YouTube channel by Ted Rogers, where he has a lot of QFT related and stuff, and also on PDFs and factorization. So if you want to have a look, I really recommend. Okay, so you've seen the motivation. So what is a proton? What do we need to understand the proton? So that's the idea of PDFs. We need to understand the nature of proton, non-perturbative nature of proton in terms of quarks and gluon, and go from this picture of, I suppose someone covered the quark model when you have three valence quarks in the proton, to go from this picture to collisions. So that would be collision with CERN, LHC in particular, and then you would have proton here and the proton there, and then all the smash happen, right? So the idea is how much does this picture that we know will evolve this picture of the proton matter for this kind of processes. And that goes through PDFs. Okay, so we go back to things that you've already seen many times. So I'm going to ask you again, but that's a departure from point-like behavior, right? But here I decided to start with a spin zero non-point-like particle, like a pion, okay? And in that case, you can try to define, that would be if you have the electromagnetic current, and if you have point-like particle, you would have this kind of behavior, okay? So that's the current, okay? How do we describe the current? Yep. I will put on the next slide, but how do we express the current, electromagnetic current?
It's with the gamma matrix, so psi, gamma, psi.
Okay, wonderful. Psi, gamma, mu, psi. Okay, we have one Lorentz index here, and that's for the pion. It's pseudoscalar, so it's a scalar, so we don't have spinors, and so the only possibility you can have here is to have, you have p prime and p, so you do have momentum transfer here. The only thing that you can build is actually this one here. Okay. And if you want to actually define, when you go from this point-like behavior to a non-point-like behavior, you want to extend and you define the form factors that I'm sure you heard about yesterday. Dan covered that a bit, right? I saw that. Okay. So you have this blood here, and you want to put a structure in that. So in the case of the form factors, it's still elastic scattering. We don't break anything, but we want to actually check what kind of structure we have. So there are two main things that we use, and I always tell my students in QFT, two big words: Lorentz invariance, current conservation. Sometimes you can also use, it's called Watt identities, depending on the book. So if you do Peskin, every time Peskin says Watt identities, mainly current conservation, they are related, they are not exactly the same all the time, but that's what I use a lot, okay? So by Lorentz invariance, you know that you have one vector here, so index mu. So you need to build all possible 4 vector structures that you have here without any spin, okay? So you can have just the sum of those 2 momenta or the difference of the 2 momenta, right? And in principle, you could have those. And you know that the structure that you have here can be multiplied, of course, by the charge. Okay, forget about the charge. That's straightforward. But by what I call Lorentz scalars, okay? Everyone, Lorentz covariant, Lorentz invariant. Difference between covariant and invariant? Yes?
The Lorentz invariant means the quantity will stay the same and draw the transformations, and covariance means it will follow the Lorentz transformation rules.
So yeah, in Lorentz covariant, basically you could have like scalars. It's basically you can check these contractiles, right? So it's what I call Lorentz scalars, it will be Lorentz covariant. Okay. So it means that when you have an index mu, of course, I mean it can change, but you have the index. And while a Lorentz scalar like a mass or the momentum square, in that case, will be invariant. Okay. And so we have 2 structures according to Lorentz invariance. Okay. But then we have to check current conservation. And I forgot the hat. Okay, forgot the hat. Okay. And that's in coordinate space. And then if you put it in momentum space, you can check. I mean, you can do that as a homework, that you would have the difference of p prime minus p contracted with the current gives you 0. Okay. And so you write your structure here, you put F1, F2, A, B, whatever you like. And you realize when you impose that this structure must be 0 because it gives you Q squared goes to 0. Okay. B Q squared goes to 0. Everyone follows that, or do you need to do it in Blackboard? Okay, so it tells you that only this structure survives for the spin 0. Okay, and that's how you define the electromagnetic form factor for the pion. Only one. Okay, no spin, only one structure. Yes.
So in the last equation, I have seen equations where this psi bar and psi are not taken at the same space point, but at c over 2 and minus 2.
That's where we're gonna go for PDFs. Okay, so that's a local operator because it's still an elastic scattering, and that's the form factor. And actually, so Dan talked about TMDs, and some people asked me. So I asked the students, "What do you want?" My students, I know, I have seen before, 2 weeks before. What do you want me to talk about? And they simply mentioned this on GPDs, right? So here, so the form factors are local operators. Okay. When we go to PDFs, you see they're non-local, but they can be related, of course. And if you take GPDs, I will mention them at the end if I have time. Actually, GPDs will be related to the non-local part of this thing. Okay, into the form factors. Okay, form factors. what you see is that the probe just tickles a bit or a bit more than just tickling, but say that we don't break the pion in this case. Okay, so now we go. Yeah, I gave you the answer. I put it here. So now we go to spin 1/2. That's what you heard about yesterday, this morning. Spin 1/2. So in that case, the proton. Okay. So in that case, we can use spinors. So we have more structures. Okay. So that's the current, but I forgot to put pion before in here, proton. So it's a proton. So we have P and S, okay, spin. And so you can build, so that's how you would have. So there's a difference with respect what we had for the pion, because in the pion, since it was a scalar, we had only this structure. Here, we do have, sorry, here you go. We do have spinors, okay? So that's the proton spinors. And in that case, Lorentz invariance tells us that we can have 4 possible structures. So the same as before, P plus P prime plus P, P prime minus P. We can have gamma mu. So gamma mu is the Dirac matrix. Okay, so in that case, we do have spin. So that's, if you like, it's spin space. Okay, Dirac space is spin space. We project them to the spin. And you can have sigma mu nu q nu as well. Okay, everyone agrees with that? So those two are new. And then you also have to multiply with Lorentz scalars and stuff like that. And you do the same thing. And it leaves you with three structures, but only 2 of them are independent. Okay, so the one that goes away, this one goes away again. Okay, and you're left with this one, and this one, but only 2 are independent. And you go to what is called the Pauling Dirac form factors. So there, yes.
What about the RPC value?
Yeah. That's okay. That's the homework. We can do it now if you like. Okay. So show that gamma mu, P plus P prime, and sigma mu nu q nu are not independent. Answer right away. Everyone? Anyone? There's a really famous identity that connects them.
Borderline.
Yes. What is the identity? Can I erase that? No, I'm gonna let me just. Okay, so you guys help me, right? Okay. I don't hear anyone hearing me. Helping me.
Yes.
Right, because okay, there must be a matrix to M, right? Plus I sigma. I'm checking factor of 2. I'm not sure. Okay. That's the homework. You have to prove that. Okay. Watch out if you can do it for you. But be careful, right? Sometimes you get it wrong. Okay.
I meant the Levi-Civita symbol contracted.
Oh yeah, you can, but then okay. So when you that's the F3. I forgot. You're right. Okay, so Pavel mentioned there was a third one, and you can have it. So I forgot to write that here. In principle, you could have parity vitality part, right? So in that case, we don't have that for form factors because Levi-Civita is a pseudo, right? This is not a pseudo tensor. But that's a good question. That's how F3 appears in the interceptor function. Yeah, but you're right. Okay, more questions about that? So there are 2, like you have you can relate those to the magnetic and electric part of the form factors. So there will be GE and GM that I think Dan mentioned yesterday, right? So you have a spin, then you have 2. Okay. Okay, so now we're gonna break the proton. Are you ready? Almost there. Okay, so before we break the proton, we're gonna do electron muon. It could be plus, minus, whatever you like. Okay, so all the textbooks start with the electron muon. Why? Because we know quarks are spin 1/2, but at the time they didn't know. But that's why there's a line thread that people follow, right? So those are all spinors. Okay, Fermi fields, and that would be the process. Time goes that direction. Be careful if you use Peskin goes the other direction. Okay, and that you've seen that many times. That would have the cross section in the lab. Okay, and I always remind students the amplitude of this process okay? That's here, okay? The cross section is proportional to the amplitude squared, okay? So I copy, paste, and invert it, okay? So that would be M star, okay? That's what you would have. That would be this line here, okay? That's the cross section, the amplitude squared, okay? But what you can also, so that usually when you calculate that and you put it square, okay? But what you can also do is that instead of just putting it square, you put it square right away and you separate that. That's what people mentioned many times yesterday and this morning. And you would have the leptonic tensor, that would be the upper part, and not yet the hadronic. So that's the muonic tensor in this case, okay? So that's a muon tensor here, okay? I did not put it, but it's straightforward to calculate that. And so you can cast this cross section instead of having the amplitude squaring it. You can cast it into the contraction of two tensors. This one for the leptonic part and the muonic part. Okay, and it gives you the same result. I'm not sure about the factor of 1/2. Okay, in my case. Okay, but it should work. Any question about that? So you guess that why we do that? Because we're going to do that for the hadronic tensor. Okay. Okay, now so that's for the point-like part. But as you've seen before, in the case of the well, I've not mentioned that. The elastic part, or even the non-elastic part, is that you expect corrections here A and B to account for the structure, the blobs that we had before, right? You expect A and B. So in the case of form factors, you can also have something like that if you like. But in the case of structure functions, it will depend on some variables. Form factors will depend on Q square because that's not the only thing you have, and they will modify these two structures, okay? And then for non-point-like particles, because that's the form factors, and then we can also go to structure functions, okay? So now let's break the proton. So that's for the point-like, you don't have A and B, okay? And for the non-point-like, you would have modification of the blob, of the vertex, if you like, okay? So we have to find A and B, okay? So let's break the proton, okay? We break it. So we know we have two structure functions, okay? This doesn't change, Lorentz is the same. But here we have different things. So we have different Lorentz scalars. So before, in the case, I forgot to put it, but I think it's easy to understand. Okay. Here I only mentioned those Lorentz scalars, but only the mass, because p squared and p prime squared will give you the mass of the proton here, right? They are the same, okay? P squared and p prime squared are the same. Do you all agree? Wonderful. But here we break the protons, so they're not the same anymore. Okay, so that would be what I call, I didn't put that, px, p prime, okay? And that's the invariant mass W squared, okay? So in that case, the p square of the initial proton here won't be the same as the invariant mass of the final one, okay? So we need one more invariant, okay? Okay, and I call, so in elastic scattering, you have q square equal to 2 times p dot q. You can check, actually. It gives you what I call nu, okay? That's what I call nu. Many books don't call that nu. I call that nu. It is dimensions of energy squared because it comes from Jaffe's reference, and it's so convenient to forget about the mass, okay? And basically what you can write in the case of elastic scattering is that you have the invariant mass square, which is p prime. So p prime is p plus q, okay? Because you have the photon coming with okay, Q, P prime, okay? So P prime is P plus Q, okay? Everyone agrees, right? And so that's what you have here, or you can write it this way. So you can see that you need an extra invariant, and in our case, we're gonna use Q square and nu, okay? Nu is 2 times P plus Q, okay? And so the same as before, but then we have 2 different invariants, okay? And so you can rewrite, so those would be A and B that I had before. Again, I try to check the dimensions, okay, but sometimes they don't work out, okay. So that would be W2 and W1, okay? And again, what you can do, so that's what we had before, okay, from the reasoning that we had. But again, you can do that. So you can take this amplitude, you square it, okay? That's the same line I had before. But what you can also do is that you can cut that way and write the leptonic tensor, which would be about the same as the one we had before. And that part here with all the blobs, okay? That's the broken proton, okay? And that would be the hadronic tensor. Okay? Everyone agrees? Questions about my cartoons? Okay. So now the big thing is, what do we do with that, right? So that's the question. And that's what Dan, Fred, and Pavel talked about yesterday. I'm trying to be a bit more in detail. Okay. Okay, so this hadronic tensor contains a blob, and we need to understand that, right? So how do we decipher that? So we have the hadron as a bound state. So because there's something perhaps we haven't said, why such a fuss about that? Because, well, the proton is a bound state, and we don't really know how to account for that, right? Otherwise, it would be solved, right? It's just a problem QFT, and then that's it, right? But it's not point like it's a bound state. We don't know what is the dynamic that binds it. And that's why we have to go through all this thing, because we don't know what to do with it, right? Okay, so that would be the expression, okay? So this, it will still come from the amplitude and the amplitude star, okay? So that's what you have. So you do have the sum over all possible x's, okay? Everything that's there. Let me just go back here. That's this unitary cut you have here. That's like unitary cut you have here, okay? So you have the sum here over all the x's. One current, two currents. So you have mu and nu, two indices. You have to conserve momenta, of course, okay? That's really important. And this expression, okay, so if we knew about the bra and the cat, easy peasy, you just calculate it, that's it. But the point is that we don't know what to do with those, okay? So what we're gonna do is try to understand what we can do with that, okay? And so what you can do is go into a more manageable expression for that, okay? And you can use translation. I think Dan mentioned that yesterday as well. I saw the slides, right? You can use translation invariance, okay, to go here. Then the usual trick of physicists there, you use, well, you use the Fourier transform of one, okay? What is the Fourier transform of one? It's the delta function, okay? So that's the usual trick that we use. So this delta function becomes a Fourier transform, okay? And that's how we go into, so that's momentum space, and here under the integral, we're going to be in coordinate space, okay? That's what you do, and then use completeness. Once you're done with all those things, you have completeness, and you end up with that. And you can actually take even the commutator of that, because the other part will cancel, okay? Okay, so that's how we go to bilocal operators. I don't know who asked the question before, but that's how we go. Just because you shift it, you translate it, this current into this one, okay? And that's how we get this hadronic tensor in terms, so it's momentum space, and here we have coordinate space. Okay? Questions? It's just a Fourier transform of one. Okay? So now we have the operator definition of the hadronic tensor, and we have to match to the Lorentz structure, right? Because we have mu and nu, okay? So what I've done before, it's actually, we have only one index, but now we have a tensor, right? And you can do the same thing. Actually, that's also a homework. It's in Aitchison Hay, right? You can do it. And you can actually check that you have those two structures that arise. And one of the problems that I let you to do for tonight, if you like, is show that those two structures emerge from Lorentz invariance and covariant conservation. Okay? Everyone knows how to do that, so you want to discuss it later? Okay. And then you do the same thing, and then you contract with the electronic tensor, and you go to the same result. I copied paste, but it works. Okay. Okay, so now we have the operator definition. We do have the Lorentz rule to match on. We can move on and do a bit more things. Okay, so now we have that, and we have nu and q squared. But as you heard before, there's a very particular regime. So we need to understand. So what we want at the end is to understand this this thing here. Where is it? Sorry. Okay, so we have this hadronic tensor. We still want to make it into smaller pieces, into scalars, okay? Because we have tensor. We would like to have the structure and the scalars, the scalars would be the function, the structure functions, okay? And try to analyze them. And to understand that, first, we need to understand the dependence on nu and q square. And you heard yesterday that we have the Bjorken regime in which nu and q square goes to infinity. And the ratio of the two is finite. It's called xp, x Bjorken, okay? And it's between 0 and 1. And I think that was one of the problems that you solved yesterday during the recitation. Is that right? And so the function actually scale, okay, and they give you F1 and F2. Okay, so I think that's, you've seen that before, okay? So now as put here, I think that both Dan and Fred covered that. So, and it was proven, and there were Nobel Prize and stuff like that. And you can see that the Slaughter function does not depend on Q square, okay, but it scales. Again, new changes from my definition to the definition of many people. I apologize for that, okay? But okay, believe me, it scales, okay? And so what it means is that's a pattern model that effectively the patterns behave as they were not interacting among each other, okay? So what you have is that inelastic scattering of a hadron is equivalent to the convolution of elastic scattering of partons, okay, with the momentum xp, where x is a fraction of the target, the parent hadron that I called, okay? And why a convolution? Because you have to convolute with a priority to find such a parton I call I, okay? So you have inelastic scattering, and you have the sum over coherent sum over elastic scattering here, this one here, okay? That you know how to calculate. Convolute it with the priority to find that that parton here that is interacting elastically, okay? And that's the naive, that's still the parton model, okay? And that F sub I is actually the PDF, okay? So note that's the picture that we saw, but we need to put a QFT definition to that, right? And the proper way to do that is through factorization theorems, but I will not do that. I will first in the parton model, I will talk about DOP, okay? So that's the idea we have, but now we have to go from what I put before this hadronic tensor to exactly write something in QFT, okay? So it's not just hand waving. It's really like, there's really a QFT definition that you can do, okay? So far we just mentioned photon probes. So that's what we had here. So in the case of the photon probe, yeah, I have an integral, so it's the charge, okay, squared, and you do have this this delta, okay? So in that case, x, which is the momentum fraction, and x Bjorken are the same leading order, okay? That's leading order. And then you can do that for a neutral current, charge currents, and all those things, and you can write all those fancy sort of functions, okay? That's extremely interesting. Okay, so now more QFT. Okay, we are in four dimensions here, okay? Sometimes 4 minus epsilon, okay, but we stick to 4. So it's always a question that I ask. So Lagrangian is dimension 4, so the bracket will be dimension, okay? So the Lagrangian density, as we should say, is dimension 4. The action is dimension 0, okay? So when you go there, it tells you that the how do you call that? The help me.
The measure.
The measure, yeah. It's as I mentioned. Well, mine here it's so that's coordinate space, okay? -4, which makes sense, right? Okay. The measure is -4. So question. Dimension of a scalar field, dimension of a spinor. First scalar field.
1.
Okay, 1, wonderful. Why? Because let's go. We can write this Lagrangian density, just the kinetic term, okay? And you can calculate, so it should be 4. Mass is 1, so mass square is 2. So phi square is 2, so phi is 1. Everyone agrees? So it also means that the derivative is 1 as well, okay? Okay, wonderful. Spinor, I couldn't put a slash on keynote, I don't know why, okay. So spinor, then you have, so mass is 1, okay? So psi bar psi is 3, so psi is 3/2, okay? Everyone follows that? Wonderful. Okay, let's go back to the hadronic tensor, okay? And so you would have, so I put, you can show that the commutator is actually, the other part of the commutator goes to 0, so you can put the commutator here. And you heard about, so we're gonna talk about what's under the integral, so it's coordinate space, okay? Usually, when you want to prove factorization, you do that in momentum space. That's what Bible say. You need a really high scale, which will be Q minus, whatever you like, okay? So that's the icon, okay? And you want to have causality, okay? So you need, So the deal here is that you have, this is coordinate space, the Fourier transform, okay? And you want this object to well behave, not, so this guy could oscillate really, really fast, right? We don't want that to happen, okay? And we need also to have causality because of the commutator, okay? And so you check what you can do. So what you heard also before is that you can put, okay, this is the definition of the icon, okay? So the vector, so the plus, so it's p bar, okay? P bar mu, and it's proportional to p. P goes to infinity, okay? And it's 1 over p, okay? And the transverse momentum we don't care about here, unless Dan asks us about TMDs, but we don't talk about it here. So you want causality, and you also don't want this guy to oscillate too much. And so you put the proton in that direction, okay? It's here, okay? Cubes. Of course, you need to make sure that it's on the mass shell, but okay, mass is really small with respect to infinity, so you can also remove that. So the proton is mainly here, okay? So, sorry, problem. Find Q mu on the icon. So we can discuss that later. So the way you can find it, well, you find Q mu is about -x on the plus direction and almost nu on the minus direction, okay? So this one goes to infinity. And what you want to calculate is, I forgot to put a dot here, okay? So it's Q dot psi, okay? And you can get to this thing here, and it oscillates unless psi plus is almost 0, because otherwise you would have infinity here, and this one is not too large, okay? And so when you put all those things together, it tells you that you must have psi square equal to 0, okay? And that's the definition of the light cone. Everyone agrees? You have to go a bit through that because, okay. And so basically what it tells you here is that if you don't want this thing to oscillate and this object to be well defined, from this point of view, you need to be on the light cone, okay? That's what we have. Okay, so what you heard before is that Pavel mentioned you need large momenta. So what you can see here is that large momenta, actually, that's how you really prove factorization, okay? But here we can also think of it in the dual space of short distances, okay? So this object is a coordinate space, okay? And it gives you hints on the behavior of the operator level. That's important. Okay, so now we've done that. We still need to, okay, we know that this is on the light cone, but we need to work this subject out, right? We need to work it out. Any question about it?
Is there an alternate route where you re-rotate this variable, this Fourier transform?
You want to do what, sorry?
A weak rotation so that I don't care about the oscillations and I have suppression.
You want to go to Euclidean space?
Yes.
You can ask your lattice colleagues. That's what the problem is. Okay, so what would be psi square equals 0 in Euclidean space? It's 1 point, right?
Yes.
So you can do that. That's the problem they have in the lattice, right? So I don't know if there will be lectures. Are you guys going to give talks about that? No? Okay. So here, the good thing is light cone in psi square equals 0, but Euclidean space is just 1 point. You don't have the light cone, right?
It's hard, but like the feasibility.
Well, you have 1 point, you can't move from there, right? So you don't really have the coordinate system. And yeah, but that was a good question. Okay, so sorry, let me just count again, dimensions. Okay, everyone is following. So dimension of the current. Psi bar, gamma mu psi, 3. So we have 6. Brackets together is -2. Everyone knows that. So we have 4, -4, 0. Okay? Everyone is following me? Wonderful. Okay, so this is dimension 6, okay? So let's work first to the this product, okay? Of course, after we're gonna take the time, order and all those things, okay? So everyone, you heard yesterday and this morning about the OPE, okay? But do you really know what it is? What is the OPE? Silence in the room. Okay. Okay, so okay. So the OPE is Wilson is it was really famous for them. He was the father of what became lattice, right? So if you have a product of 2 operators, then there have to be currents, okay? 2 operators here I use because we have currents, and they are bilocal, okay? But if the distance between them goes to 0, here is the distance, then you can extend to the line code distance as well, right? Then you can actually expand it as a sum. Okay, so there will be different terms. A sum of that contains each of these terms contains factors that is singular. Okay, those are the Wilson coefficients that you heard about yesterday, this morning as well, multiplied by a regular operator. Okay, so that's each of those terms will be like that, and they're ordered by the singularity. The most singular one first, the less singular one afterwards, and all those things. Okay.
That's singular.
What?
What does it mean they are singular?
It's a good question. What does it mean, the singular? Singular.
Diverges.
It diverges. So if I have, for example, 1 over xi goes to 0, what happens? Sorry?
Diverges.
It diverges, right? Okay. And so you would have things like that happen. Okay. And
Is that divergence is inside?
it's, yeah, xi, yes.
So it's not on the y, but kind of divergence.
Well, so let's work first in xi and see what happens in xi, okay? And then we can go to other things when you think. So in terms of xi, so you want to think about when xi goes to 0, momentum goes to, so the distance is small, then momentum is large, okay? Everyone agrees? Okay, so we see what happens. So as I said before, this is not the proper way to factorize, but that's a tool that is used in many tricks that's used in many things. For example, if you think about E plus E minus, it's really used a lot as well. But if you want to really prove factorization, you should go to Colin's book, okay? Not that, but that gives you an idea of what's happening, okay? And so, for example, you want to have, did I put the diagram before? Let me just, oh. So that's the amplitude you want is squared, right? So you imagine you just square it, okay? Can you see it here? Whatever happens here, you'll know. Okay? That's the one we had before, right? Okay. And okay, and so what you want to have, as I said before, you don't want to do that. You want to have tensor here, this new tensor here is already factorized, but then here you see that other things very well. So, okay, we have the leptonic tensor here, so that was the leptonic tensor, and all that is the hadronic tensor. Okay? But still, this hadronic tensor, we know part of it, okay? And there are parts of the things that we don't know, right? So we want to go to that.
So is this a finite series or an infinite series?
Sorry?
Is this a finite series or an infinite series?
Well, you can expand. I mean, depending on the operators you're gonna have more or less terms, of course, right? But depending on how, so if you have some operators that have these kind of divergences that will contribute or not, singularities, then you would have more terms than if you don't have, right? But in principle, depending on the operators that you will have, right? So, but we're not gonna use all of them in the first time. I mean, okay. So now we talk about dimensions. We can have that for the recitation. We can have the dimensions of C and theta. Otherwise, I'm not gonna finish. Okay. So, for example, here, if you take this, we have the hadronic tensor here, and we want to find part that we know and part that we don't know. And we can see here if we have a propagator here, okay, that would be dimension 3, okay, and then you would have what's left here, okay. So you can actually, in that case, what the first contribution to this thing would be a propagator here, and then the rest, okay, and that's how you build this handbag diagram from the operator product expansion. Okay, so it's not the same thing as factorization. So you would have this and the rest. Okay, and you can do that. And now, if you want to really expand that, okay, you take the time order product of this. So this you've done, you all know Wick theorem and all those things, right? So I have to do this time order of 4 fields, okay, because I see psi bar, gamma mu psi bar, gamma nu psi, okay, and it gives you all sorts of stuff. You can work it out, okay, And it will give you, the first will give you, you will have a propagator, which is the one we had before, the one that we introduced, propagator that is there. Where is it? Okay, the propagator. And you will have this type of stuff, okay, of bilocal current here. And you can do two different things, okay, from this point of view. You can keep it bilocal, okay, or you can do, you can fully expand it this way, okay. Both will be somehow related, of course, and you can expand it this way. And the reason I'm going to show that to you is because there's something interesting. And so then you can write this. You go back to your hadronic tensor. So you take this, you sandwich into the things. You have all the traces you need. You have the singularity that we had before. So it's the propagator in coordinate space. You do that. And here, instead of keeping this one here, you expand it, okay? And you define, this is they are local, okay, operators here. You define them as what I call the moments, okay, many moments, and then psi comes here, okay? And you can actually calculate the operators and this expansion in terms of what's called a twist, okay? And you can show that the lowest twist that contributes is twist 2, okay? We can go into that into the recitation if you like. And if you do this, okay, so in the OPE, you work that out, okay? And you, as we said before, we said like psi plus was 0, and now we say that we don't care for now about transverse momentum, we just forget about them, we go linear, okay, we assume it's 0, we put this to 0, and you end up with this object here, okay? And there will be, of course, some Lorentz structure that multiplies that, okay? And you take that. And that's how you got to this definition of a PDF from DLP, okay? So of course, it doesn't take into account many of the things that happen, but it gives you at least an idea of QFT, where it comes from, okay? And then if you follow this, the same thing here, you would have the same structure, and you actually can relate to the Mellin moments of the PDFs here. Those are the subjects, okay? And something so that was defined a long time ago by many people, but there was a revival of interesting things lately because of lattice colleagues. And this product psi p, okay, so it's 4 vector is called Yoffie time, okay? So in the case of PDFs on the Lycon, this psi p would give you p plus psi minus, okay? P plus psi minus, that's what you have here, okay? And you can actually show that you can, so that you can do this, it will be an equivalent of, it's not exactly an inverse Mellin, but an equivalent of that. So you can, in principle, have the Yoffie time expansion of PDFs, okay? So there was a hint for lattice colleagues because lattice is becoming more and more important here. So I have to speed up, sorry. Okay, okay. So that's the summary so far, okay? Now the question is, what is a PDF? So that's, okay, we got the definition, and so you go to this, I don't remember which textbook, is one of the old textbook. And so if you have just a quark, that would be the, what I call then the, so it would be the elastic case, if you like, or just like the Patternick level, if you like. If you have 3 valence quark and nothing happened, there are just 3, you would have 1/3. There's absolutely no model ever that gives you that, because no model is so crazy just to give you like 3 quarks. But then if you take non-perturbative models, because what we miss basically to evaluate this object here is the expression for that and the field that go into that, right? And that's why you can take models for that and you can evaluate. Actually, I relate it as a problem. And you can take, for example, the MIT bag model, you can take some Schwinger-Dyson method, and they will give you like a smeared delta. So that would be a delta, a smeared delta, around 1/3. Okay? Then of course I have a question for you. And then you have, and that's only QCD, right? So this would be at a specific scale in which we have 3 valence quarks, right? And as you heard before, those 3 valence quarks, we don't know where, at what scale it happens, right? It might never happen. So I mean, we have 3 valence quarks all the time, but only 3 valence quark and nothing else. It's something that might not, we don't know at what scale it happened, right? So this is really, this is a pictured fixed Q squared, okay? Well, we know that in QCD, you would have Of course, you expect the valence with low scales to have this kind of behavior, but of course, then you will have gluon emission and pairs emission as well, okay? So I'm happy to let that as a homework. Definition of PDFs. You can also go to the same definition that I showed before. You can go to Ted Rogers' YouTube, and you can use the number density operator, and you build wave packets and stuff, and you can define a PDF F1 as coming from this number density. Okay, so I will leave you to do that. And another problem that I will let it to you if you want to come back to it, you can ask me later. You can use models, okay? You can say that the quarks actually are confined, okay? They're confined in a bag, and you can have this, what it gives you is boundary conditions on solving the Dirac equation. That's the bag model, if you like. You have Bessel functions, and you calculate that, and it gives you a straightforward, that's TMD, but just integrate over KT, it's fine. And it gives you a shape for the PDF. Okay, so if you want to discuss that later, then we can do that. So that's where you go from the operator that you have. You can use a model for the spinors and the wave function of the proton and calculate something. Okay. Now let's go back to real world. And at low energies, QCD cannot be solved in perturbation theory, as you know, and so we cannot really calculate those objects. And what we've said is that it needs to be data-driven analysis or ab initio evaluation, right? And before we do that, we have to go to QCD, okay? So you heard about that before. I'm gonna be too late. Okay, so scaling, okay, PDFs. You've seen that that's F2. You have approximate scaling and you have scaling violation. So we said that in the Bjorken regime, there's no dependence on Q square, but what you heard before is that there is dependence on Q square, right? So in the parton model, you would just have partons that interact, perhaps not, okay, and they don't depend on Q square, but in QCD, any of those can then radiate gluons, which in turn will radiate pairs, quarks, antiquarks, and stuff like that. And this picture emerges, okay? I think you've seen that before, and you can also put that in parallel with what happens with alpha S. I'm sure that Pavel mentioned that before. You mentioned it yesterday, right? And so you know this picture already. Okay, so now, okay, I'm sure you've seen that in the intro lectures, but let's go back to simple things. The normalization, okay? Everyone has seen normalization? I mean, besides what you heard. Okay, so let's do a simple thing. You can define in QED an effective charge, okay? I mean, if I can't summarize that in 2 minutes, but you take that's the vacuum polarization, okay? So you would have a renormalized charge, which comes as a condition, okay? So you put a condition. You say that the renormalized charge is the effective charge at some momentum P naught. Okay, you choose. That's the condition you put, okay? And you go to the textbook, that's what's the textbook. The textbook, and you know that you would have this, and then you can show that you can actually have a series of that, okay? And you see it's an expansion, okay? So you know that this expansion comes from some function that you've expanded, okay? And we want to resum that, which is doing the opposite of expanding, okay? And you can write those, and you will see that we can actually do that. You will have the logarithm, so you have 1 plus some factor, the logarithm of p squared over p0 over p naught squared, etc., and that's the Taylor expansion of this function. Okay, do it once if you've never done that, because that's really interesting. Okay, so that's what you get in the textbook, but you can do something else. It's equivalent to demanding that the effective charge P, okay, does not depend on the momentum in which you put the condition of normalization. Okay. So you decided to put P0 here, but it's kind of arbitrary, okay? So physics should not depend on this P naught, okay? So you demand that this object on the left-hand side does not depend on P naught, okay? And that's basically telling you, so that's what you heard before Pavel say that this left-hand side, this derivative with respect to the log of P naught or P, or whatever you like, is 0, okay? And you do it and you find the same solution, okay? And that's the idea behind the RGEs. Everyone agrees with that? Yes? Okay. So this main idea is what we do. That's how we go to DGLAP as well, right? Okay, so that's what we heard before. So That's again, that would be, okay. So now we separated those things. We have the leptonic, the hatonic one. We have, there's no color here. And we know that this will be the PDF, okay? More or less. We don't know yet where it gets, okay? Somewhere here will be PDF, and there will be this other part here, okay? And to understand where we put the limits, we have to look at what's happening here, okay? So what I said before, in the case of DOPE, we just stick to this one here. We didn't care about anything else. We had that photon and okay, so we had that's the photon that's here. Takes momentum, so we said XP, but now we're gonna put YP because we want to change a bit, we don't know it's X yet. And then you want to put corrections into that, okay? Then you do the corrections, you will have the real contributions, okay? This will come, they need to be squared, so every vertex is GS. So alpha S is GS squared, so it comes squared. And this one you have alpha already, right? So they will come in interference, okay? And you have the gluon emission as well. So you do that. And you put it back into F1, F2, the one you prefer, okay? That's the diagram I showed before, right? And so you had, remember that I had this incoherent part, okay, the elastic scattering. So what I call F1 hat is the partonic level here, okay? So that's the F1 of the partonic level. So that part here is F1 hat or F2 hat, and the whole thing is F1. And that would be the PDF F1 sub I, okay? Little f, capital F, okay? Capital F is the sort of function here, okay? And so before that's what we had, it was straightforward, it was just E, the charge squared, but now we have all those corrections, okay? And so we calculate those diagrams, we calculate those corrections here, and I put some band here, what's gonna happen, because we have to decide what's gonna happen. And you can calculate all those things. It's similar to Compton scattering, okay? If you take Compton, just that one is a gluon and the other one is not a photon. Okay, take gluon here. You calculate the Mandelstam, they're here in the center of mass, for example. You can show those things, and you realize that there's just one diagram, okay? And you realize that you can write it this way, okay? That will be singular part and non-singular part. So here, when Z goes to 1, you will have problems, and when theta is 0, you will have problems as well, okay? And so you could have those things, okay? And then you can show that it can be proportional to the, if you put, so here you forgot about the mass of the quarks, you put back the mass, and you can show that it will give you something about the log of Q squared over M squared. And this function is called, it's almost a splitting function. It's the real part of splitting function here, okay? And then you would have the splitting function multiplying the log of Q squared over M squared plus non-singular terms, okay? That's what you do. That's for the real diagrams, okay? For the virtual ones, you can show that they are proportional to delta function, okay? So they are the endpoint contributions. And you can find this whole splitting function. That's just for quark. You have many other functions that you can do too, okay? But the important thing that I want to show, since we talk about factorization, is that this log, so you have a small mass, so it's or you can put KT if you like, okay, like a small scale, okay, non-perturbative scale, and Q squared is supposed to be large, okay? But you can split into 2, okay? You could have you decide that you want to have in between the 2 an arbitrary scale that's called mu f, okay, for factorization. You can do those things, okay? And then you just put all the things together, okay, back to where it was before. Where is it? Here, you take this, you've calculated this one, okay, so that's just all those diagrams. And you put it here, okay? And then you say that this corresponds to low energies, high energies, okay? It's arbitrary, you cut, but you do it. And then you put one part into the PDF, okay? That's what you call the renormalized PDF. And the other one you put into the partonic level F1, okay? Capital F. You do that. Okay, sorry. Okay, and then you still have to decide what's going to happen, right? So the sort of function, as Tavo said before, should not depend on any of those arbitrary scales, okay? So this guy does not depend on mu, okay? So you need to actually demand that F2 does not depend on mu, so this derivative respect to the log of mu is 0. To do that, okay, this is straightforward, but it means that if, so what happens here with mu F must be compensated here, and I forgot to put mu F here, okay. Yes, this guy should have mu F as well, okay? So what happens here must be compensated by what happens there, okay, with mu F. And that gives you exactly the Diglap evolution equation, okay? You can do this exercise, and of course it's more complex because alpha depends on some scales as well, right? Okay, but you can do that and you find this evolution equation. It comes from demanding that this guy does not depend on LU. So that's the same idea behind RGEs. Okay, at the end of the day, the PDF, so what you will do is that mu F will be taken to be Q squared, right? But they will still have the same kind of equation that comes from the same concept of RGE. And we have all these complicated names that I won't pronounce because, okay, yeah, Diglap, okay? They come from here. That's basically what we had. So as you heard before, do I still have time? 5 minutes, right? I discussed QQ, so it's called the non-singlet, okay? So non-singlet is often related to what you call the valence. Okay, it comes from the group theory definition of singlet and non-singlet. So you have Q minus Q bar, but you can also have the singlet, and that's a couple equation of NF, okay? So the number of flavors that you would have, all the flavors you would have, and the gluon, okay? So that's a very complex integral differential equation, okay? There are programs that solve them for you, okay? It's some that's next to leading order, just alpha S, okay? Then of course you can mention more. And then the gluon will come as a combination, as you can see here, of the singlet and the gluon, okay? And other things happen. So the non-singlet does not mix with the gluon and those, but those guys mix, okay, to this equation. That's important. And I will talk more about, so Pavel already mentioned the initial conditions about mu naught or Q naught, whatever you want to call it. Tomorrow we're gonna talk about that, what it means, okay? And so far we discussed next to leading. I put some slides in the backup with some of the equations if you want about other higher orders, but the concept is the same, just that you have to calculate the splitting functions, okay? And that's a bit more complex, okay? And then there's also more than just that, many others, okay? Okay, so now the Diglap equation, talk about factoring scheme. And so you heard before about the renormalization scheme as well. So how much finite contribution we let into the PDF that we don't know it, right? So we put things, we don't know what it is. So we happily put things there. That defines your scheme. So someone mentioned before that there was no FIS correction. That would be the DIS scheme, okay? And Pavel will talk about heavy quark schemes tomorrow, but the MS bar scheme is that you put these usual factors absorbed into this one here, okay? And that's what we use, okay? And that allows to have what we call the universality of PDFs. Once you go through factorization theorems, you prove for each process that you can get to those observables and that you would absorb this part, that MS bar scheme, okay? And you can plug them into other things. Okay, so now about the evolution, I still have 2 minutes. So that's it. So now we can emit gluons and pairs. So what's going to happen is that there are more and more patterns that are created, okay? And you create more patterns. And so the momentum fraction x of the parent hadron will be shared among more patterns. So what's going to happen? If I have an initial shape around one third, we say 1/3 because we imagine that we have a model, we have only valence quark, and each of those valence quark takes 1/3 of the momentum fraction of the whole momentum, right? Now I have many more patterns. What's going to happen? Do they still take 1/3 each? No. They take less. So what's going to happen to the shape? Say the valence. Say if in my model I have like around 1/3, I this kind of skewed Gaussian. What's going to happen to that shape? It's going to be shifted towards small x, right? And that's what you can show. I took that from Fred. I'm sure you showed it yesterday, Fred, right? Okay, so that this is not really the balance, but they will be related, right? So you expect to have a shift. So balance will be up minus u bar, okay, or d minus d bar, okay? And so you expect to see a shift of those at lower x values, right? Sorry. And then, of course, you can see in there's more and more gluon, okay? So the gluon arises as well due to the evolution equation as well, and that will be from 1 under c, okay? So I don't know if Fred obtained those curves from which initial condition, but that gives you an idea of the evolution. Okay, almost at the end, okay? So I want to talk about thermals. You heard about thermals, but that's really important. So we have some conserved currents, okay, that leads to what we call scaling charges. By scaling, it means that the anomalous dimension is 0. So you heard about anomalous dimensions. I don't know if you know so much. So okay, so moments of PDFs are scalars. There's no reference to the icon. They are scalars, okay? So that's really important. If you take the vector current, you would have conserved number density. You have x times the unprized PDF. That's the projection of the momentum fractions on, so that's what the moments are, right? The projection of x on the PDF, divided by the PDF, or x squared divided by the PDF. So you have the momentum conservation. You have to conserve at the end the sum over all x's must give you 1, okay? And from strange PDF, there's no valence strangeness, okay? For example, that's what you have. So it translates like that. So you have 2 up valence, 1 down. As you can see, there's a scale dependence here, okay? The PDF depends on the scale, but on the left-hand side, there's no scale dependence. That's what it calls sum rule. It means that anomalous dimensions are 0, and I will show it next time if I have time. So same about the momentum fraction, the sum to 1 at any scale, okay? I mean, we don't lose any momentum here, okay? And there's never valence strangeness, okay? That's important. You can show for the helicity, and there are other non-conserved, I just mentioned them because it's important as well, non-conserved currents or projections that need to run in charges. They should not be called charges, but they are, okay? And they run, okay? So if you take some lattice higher moment, they will also depend on q squared. If you take tensor charge or scalar charge, they will change as well because they're not conserved current, okay? That's important to know. And just the last thing, so you can relate the splitting functions to the Mellin moments, okay? So the splitting function you can evaluate that one was before. You can go to this expression for the QQ non-singlet here, and actually this one is 0 because you need to conserve. So each comes up from when you calculate that. And at the level of the splitting function, we imposed that at the end, it needs to be conserved, right? You need to fulfill the sum rule. So perhaps I do not insist on that, but this anomalous dimension here, the number 1, we have 1, so it gives you x0 here. It's related to the QQ non-singlet that we mentioned before. And when we calculated the endpoint behavior, perhaps I forgot to mention it. It is such that it conserves the balance sum. That's really important. Okay. Okay. So the gap and balance sum rule. So same here. So that's from the valence part. You need to conserve the area. So this is x times the up, right? So it doesn't really work. If we would be multiplied by x, divided by x, the area under the valence curve is always 2. Okay, for the up. Okay. So you can see the changes in the shape, but at the end, the area must be the same, okay? And what you can see as well is that when you go from, that's for CT18, I will discuss tomorrow how those things are obtained. From 2 GeV to 100 GeV, you see that the gluon contributes more and more at higher scales. Same for the C, okay? And there will be less balance. Okay, I'm almost at the end. Okay, so here there's something I forgot to mention. So that will be in QCD, okay? F1, that's the gauge link that Pavel mentioned before. That would be gamma plus, so that's the spin structure from Dirac structure. And here I did not put all the indices, but there will be color indices that would come here to be conserved. So gauge invariance to the gauge link. They are flavor indices, okay? Flavor space, spin space, so Dirac space if you like. So all those things, so if you like, you have psi bar sub A in Dirac space, gamma plus AB, okay, in Dirac space, psi b, okay? So it's all like matrices, okay? In each of the spaces we have, and all would be contracted. So you would have all those indices there, okay? So you have the targets, then you depend on that. Okay, so I did not mention factorization theorem because I'm not an expert, okay? I go to Ted Rogers' YouTube channel or John Collins' book about how to properly define that with all the UV and stuff that you need to do, okay? That's really important. And then the universal is extremely important. It will depend on the process. Okay, just the last one, then we can go for lunch. PDFs are here. So that's, I forgot to put, I did not put any references to other people, but that's the usual cube that the Rossi Pasquini show. So PDFs here depend on X. I mentioned the charges. Once we take the Mellin moment, we have the charges, okay? So Dan mentioned TMDs. So if you don't stay collinear, but you allow to have psi perp, you would have dependence on K perp as well, right? So that's the intrinsic momentum of the quarks. You would be here, right? Then this space is a bit more complex. But if you take form factors are here, if you see, so if the PDF, if instead of having P and P, we do have actually an almost exclusive process, and we have P and P prime, the momentum transfer, you would have called GPD. So delta here is P prime minus P that we have for form factors. So you have P prime minus P dependence, okay? And you have another dependence on top of that, you will have GPD. So it's bilocal P prime, and you integrate over X, and you have the form factors. And this is associated by DOP. So all those definitions come from DOP, okay? And then there's the fancy GTMDs that are related to the Wigner functions, okay? They contain, so those will be three-dimensional, five-dimensional picture of the head, okay? And those are a bit more elusive to think about processes in which we can find them. And there are processes for TMDs, for GPDs, but GTMDs are a bit more complex. But that gives you the idea. And I think I'm done. I'm done for today. Yeah. Thank you. Sorry for the 5 minutes. Yes.
So when do we use the right cone gauge and when do we not use that?
I forgot to mention that. Okay. Here, usually we don't show it because I put the expression. So it contains a mu field, okay? A plus field. And of course, you need to define the gauge that you want. So if you use the Lycon gauge, it means that a plus is 0, right? So the exponential of a plus, I will add that into the slides is 1, okay? You chose a gauge. It's a choice you make. I don't know all examples in which you can't choose. So there are some examples in which you can't choose that one. The one I can think of is the Sieverts function, right? So you have TMD. There might be other examples. I don't know if anyone has more examples. If you take TMDs, there are some of those TMDs. Of course, there are more structures because you have KT dependence, right? So instead of having 2 structures, you can have much more because you have KT, spin of the anything, okay? One of those functions is called the Sieverts function. And the Sieverts function is T odd, so it's not invariant under time transversal, and it depends if you use series, as Dan mentioned before, or Drellian, because we will have finite initial state or finite state interaction. And there are gluons that come and they actually interfere with those ones, okay? And in that case, you cannot use, well, you could use it, but it's more complex to use a Lycon gauge. You should use another gauge. It's just a convenience at the end, right? I don't know if other examples of not using the Lycon gauge.
Example, so if will be using Coulomb's gauge.
Yeah, which is also more complex because it's not, this one is not covariant either, but Coulomb gauge is even worse, right? So yes.
So, when we talk about PDFs, can we get any information about the helicity? Because like in the states, the helicity is always constant.
Yeah. So the helicity, which helicity of what? Sorry.
Helicity of the parton.
Yeah. Okay.
State is of parton, right?
Yeah. So I did not mention that. So that's the unpolarized. Okay. I think I mentioned it somewhere, right? The unpolarized PDF. Because so that's Dirac space, right? So that projects on into the sum. You would have plus minus, right? But in principle, if you multiply by gamma 5, so at leading twist, there are 3 PDFs, which is the polarized, helicity, and transversity. They were mentioned somewhere. So helicity is we have gamma 5, so you would have plus, minus, 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 plus, right? And that gives you the spin contribution of quarks, right? So it's just gamma 5 here. So sorry, this one is like, so instead of having gamma plus, you have gamma plus gamma 5, okay? That's G1, okay? And then if you want to have the transversity, which would be the transverse polarization, is sigma, there must be another thing, so something with sigma, okay? And that are the 3 leading twist PDFs that you can have, right?
Do we have like this sum rules for this also?
Sorry?
Do we have the sum rule for momentum?
I mentioned them, I'm sure, okay. Because here they are, okay, yeah. Look. Okay, helicity, you have GA. Okay, axial current is a different thing. In the case of a transversity, GT is not conserved, it's running one, yes. And of course, the problem is that you need also to have, so if you change the helicity of when you, okay. So if you select a different helicity here, you need to make sure that the proton and the states here combine in a proper way, right? And so, for example, the transversity is a Carl-Hart object, right? In the case of TMDs, you can play with unpolarized target and polarized thing, but you need to make sure that this is well balanced. So the helicity that you will choose here in Dirac space will have to go well with what you have in the spin and in the target as well. So sometimes that's why you need polarized targets. For many TMD aspects, you need to polarize the target as well.
No further questions, let's roll again. We'll have a discussion section this evening, so you can say the questions. Also, on Thursday evening, we have an hour of participant talks. I think initially on the web page. If you want to do that, there'll be between 5 and 20 minutes. But and again, we'll try to people that so have a good lunch, and we'll be back in an hour.